Hey everyone, in this video we will be learning how to evaluate piecewise-defined functions. To build up to the formal definition of a piecewise-defined function, we're going to start by looking at a few examples. The first is the graph below represents a piecewise-defined function f of x. If we look at the graph, it looks like there's been two separate functions graphed on the same set of axes, but in reality that's a single function, a single piecewise-defined function, where we have two separate pieces, in this case, of the function. In order to evaluate the function using the graph, we'll use the same techniques that we've been using previously. So f of negative 3, we're looking for the output when the input is negative 3. That's the same as saying when x equals negative 3, what's the y coordinate? So we go to our graph, we go to negative 3, we go up to the function. The point is negative 3 comma 1. So if we input negative 3, the function's going to output positive 1. F of 2, so if our input is 2, what's the output? So we go to x equals 2, go up to our function. The point is 2 comma 4, so if we input 2, the function's going to output positive 4. F of 0, so if we input x equals 0, go up to the function, the output's going to be positive 2. And f of negative 1. So if our input's negative 1, our output, well, the hesitation here is because I see 2 points, one that's open and one that's closed. Now we've done a lot of work with our inequalities with that idea of open and closed, so they continue into this example. If we have an open point, that counts as being not equal to. If we have a closed point, that is equal to. So if we're looking for the output when x equals negative 1, we go to the closed point here, and the output's going to be negative 1. Now the next logical question is, couldn't it be both? Couldn't we say the output's negative 1 and positive 1? So then I'll go back up here and remind us that we have a function. The definition of a function is every input has only one output. So if we closed in the point at positive 1 here, and we tried to do the vertical line test, it would intersect twice, showing that the input of negative 1 has 2 outputs. And then we wouldn't have a function. Okay, so that's why we're only going to get one output here, and the only output is the one where we have a closed point, a defined point. So now that we've evaluated this piecewise function graphically, how would we do it algebraically? The equation for the piecewise-defined function on the previous slide is f of x equals, a curly bracket, negative x minus 2 on the domain negative 4 is less than or equal to x, which is less than or equal to negative 1, and x plus 2 on the domain negative 1 is less than x, which is less than or equal to 4. So this is what a piecewise-defined function looks like algebraically, where we have a defined function on a restricted domain. So the first thing I like to do when trying to evaluate a piecewise function is box in the domain. This just removes any potential confusion between the domain and the actual pieces of the function. Okay, so this is where our domain restrictions are. So if we're trying to evaluate a piecewise-defined function, so let's say we're trying to evaluate f of negative 3. So our input's negative 3, so that's saying when x equals negative 3, what's the output? So I consider evaluating a piecewise-defined function a two-step process. The first step is deciding what domain the input is part of. So negative 3, is that in the top domain? Is negative 3 in the inequality negative 4 is less than or equal to x, less than or equal to negative 1? Or is it in the inequality negative 1 is less than x, which is less than or equal to 4? So looking at our domains, negative 3 falls into the top domain. So that means that we're going to plug our input into this piece of the function, into negative x minus 2. So by doing that, we're going to substitute negative 3 in for x. So we have negative 3 minus 2. So that means f of negative 3. So negative 1 times negative 3 is positive 3. minus 2 is positive 1. So if we input negative 3, the output's positive 1. And again, some of you may be thinking, can we plug negative 3 into both pieces here? But then we would get two outputs. And I'll again go back to the fact that we have a function. In a function, one input has only one output. Okay, so that's why we first have to decide what domain the input falls into. So if we look at our next example, f of 0, so that's saying x equals 0, what's the output? So 0 falls into the bottom domain. Negative 1 is less than 0, which is less than or equal to 4. So that means we're going to input 0 into this piece of the function, into x plus 2. So we're going to substitute 0 in for x. So we have f of 0 equals 0 plus 2. So simplifying, f of 0 equals 2. F of negative 1. So our input's negative 1, that's our x value. Now looking at the domain, I see negative 1 twice. So now we have to look more carefully. We have to look at the inequality signs. In the upper domain, x is less than or equal to negative 1. In the lower domain, negative 1 is less than x. So if we're trying to input negative 1, we need the domain where x is equal to negative 1. So that's the upper domain, right here. That inequality sign makes the difference. So that means we're going to plug negative 1 into the upper piece of the function. So we're going to substitute negative 1 in for x. So negative 1 times negative 1 minus 2. So if we simplify that, f of negative 1 equals positive 1 minus 2, which is negative 1. And then lastly, for this example, f of 2, right, that's saying when x equals 2, what's the output? So 2 falls into the lower domain, so we're going to plug it into this piece of the function. So substituting 2 in for x, we have 2 plus 2, so f of 2 equals 4. So now we can take the outputs that we got and check them with the outputs you got using the graph, and we should see that they are exactly the same. If we have the graph or we have the function, we're going to get the same output, which should make sense. So now that we've evaluated a piecewise-defined function off a graph and algebraically, let's create a formal definition. A piecewise-defined function is a function that is defined by different equations on different parts of its domain. Okay, so if we look at the example, f of x equals 3x plus 7 on the domain x is less than or equal to negative 2. It equals negative 4 on the domain negative 2 is less than x, which is less than 1. And it equals 6 minus x on the domain x is greater than or equal to 1. Right, so we have different pieces, different little functions on different domains. Put all together, we've created a piecewise-defined function. Notice there's only one f of x. Everything's grouped together using that curly bracket. So now let's practice. So again, we'll start with a graph. So the graph below represents a piecewise function g of x. Evaluate the following. First, we have g of 4. So if we input 4, what is the output? So we go to x equals 4, we go up to the function, and we see that the output is 1. G of negative 2, so we go to x equals negative 2, we go up to the function, and we see that the output is again positive 1. G of 0, so we input 0, we go up to the defined point, not the open point, the defined point, and we see that our output's going to be 5. And g of 2, so we go to x equals 2, we go up to the function, and the output's positive 1. Now it just is a coincidence that 3 of our outputs were 1 here, based on what the graph they gave us was. Okay, g of 0, I would say, is the most difficult to evaluate because we have that decision between the open or the closed point. But again, think of graphing those inequalities on the number line, right? When you graphed x is greater than 5 or x is greater than or equal to 5, right? How did you discern between the two? Well, you made one have an open point, one have a solid point. The solid point was where it was equal to. So the same thing on a graph of a piecewise defined function. Now, determine all values of x such that g of x equals -1. So they're switching it up on us. They're telling us what the output is. We need to figure out the input. So if we're looking for an output of -1, I suggest drawing a horizontal line at -1, because those are all the y values where we could get -1, and looking for where it intersects the graph. So it intersects at that point there. So in order to get an output of -1, we need to input -3. So here x equals -3. G of x equals 3. So what are the inputs that would output 3 in this particular function? So again, draw a horizontal line at 3. Those are all the points where the output would be 3. So we look where that intersects the graph. So I see it intersects at that point there. So if we input -1 into the function g of x, we would output +3. Now we don't include 0, right? X equals 0, because there it's an open point. Right? If we plug in 0, we don't output 3, we really output 5, the closed point there. And then g of x equals 1, so we draw a horizontal line at 1. So now our point of intersection we have here, but we also have, I'll use green to overlap here, we have this point all the way here. So we have a single point of intersection, but then we have this whole long piece of intersection. So how are we going to possibly write this out? We'll determine all values of x. So x equals -2 is one of them. That's the simpler one, right? If we input -2, we output +1. And then if we input any x value greater than or equal to 2, our output is always going to be 1. So, or x is greater than or equal to 2. Right? So we literally write the inequality that represents exactly what we see on the graph. We see graphically that 2 or any value larger than it, when inputted into g of x, outputs 1. So write the inequality to represent that. And then don't forget to include x equals -2, which outputs 1 over here. Okay, so this is a little more challenging, but if we take our time and look closely at the graph, there's no reason why we can't come up with this solution. Given f of x equals 3x plus 7 on the domain x is less than or equal to -2, -4 on the domain -2 is less than x less than 1, and 6 minus x on the domain x is greater than or equal to 1. So this is that example we gave in the definition. So the first thing, if we're going to be evaluating algebraically, is to put a box around the domain restrictions. And that's just a reminder that we're going to first find the domain that the input falls into, and then look to the left to figure out what piece to plug into. So f of -3. Okay, so if our input is x equals -3, that falls into the top domain because -3 is less than or equal to -2. So we're going to substitute -3 into this piece of the function. So 3 times -3 plus 7. So f of -3 is equal to -9 plus 7 is -2. F of 8. So if our input is x equals 8, looking at our domain restrictions, 8 is greater than or equal to 1. So that means we're going to plug into this piece of the function. So we get 6 minus 8. So simplifying, f of 8 is equal to -2. F of -1. So if our input is -1, looking at our domain restrictions, that falls into the middle domain restriction. Negative 1 is between negative 2 and 1. So we're inputting into this piece of the function. Now there's no x value there. So how do I put negative 1 into negative 4? Well, we don't. What this piece is telling us is if x falls in this domain restriction, the output's just negative 4. That's it. F of negative 1 is negative 4, and we're done. We don't have to do any simplification. There's no x to substitute our input in for. Okay, so we don't change anything. Keep it simple. Negative 4 is the output when x falls in this domain. F of positive 1. So looking at our domain restriction, I see 1 in 2 different domain restrictions. So look closely at the inequality sign. Here x is less than 1. Here x is greater than or equal to 1. So if we're trying to input 1, I'd choose the bottom domain restriction. So that means we're plugging it in to the bottom piece. So we have 6 minus 1. So that means that f of 1 equals 5. And then we have f of negative 2. So again, we start by looking at our domain restrictions, and I see negative 2 in 2 separate domain restrictions. But looking more closely at the inequality sign, I see that x is equal to negative 2 in this top domain. So that means we're going to plug in negative 2 to 3x plus 7. So we have 3 times negative 2 plus 7. So f of negative 2 equals negative 6 plus 7, which is positive 1. Perfect. Now, changing it up, same piecewise function, but now for what value or values of x does f of x equal 4? Well, off a graph, that was easy. We could draw a horizontal line and see all the points where it intersected the function. Algebraically, not as easy, right? Because technically, we could have an input here that outputs 4, here that outputs 4, and here that outputs 4. So we could have 3 separate values. So that's exactly the way we're going to approach this. What we're going to do is we're going to start by setting each piece of the function equal to 4. And solving the equation we get. Okay, so fx equals 4. We're setting each of the pieces equal to 4 to figure out what input would have to be plugged into that piece to get the output of 4. So on the left side, we start by subtracting 7. So 3x equals negative 3. Divide by 3, x equals negative 1. Now, it seems like perfect, I found a solution. But what we have to check is that the x value we find is in the domain for that piece. So the domain for this piece was x is less than or equal to negative 2. I'll move that. The domain was x is less than or equal to negative 2. So is negative 1 less than or equal to negative 2? It is not, so what that means is there is no input into this piece of the function that outputs 4. Okay, next up. Negative 4 equals 4. That's never going to happen, so there's no x to solve for. If we found an x, we'd have to see if it fell into that domain. And then our last piece, 6 minus x equals 4. We can start by subtracting 6 from both sides of the equation. Negative x equals negative 2. Divide both sides by negative 1, x equals 2. Now again, considering the domain restriction for that piece was x is greater than or equal to 1, we have to check, is x equals 2 greater than or equal to 1? It is. So that's the only solution. So we did find 2 x values, but this x value was no good because it did not fall in the domain. Right? Imagine trying to plug in negative 1. Right? If we took all our work away and I said plug in negative 1, you wouldn't plug it into that top piece. You would instead plug it into the middle piece, and your output would be negative 4, not positive 4. So if you're ever unsure, you can always try. Take your x value, plug it back into the function, and see what you get. Let's do one more like this. to wrap up this video. For what value or values of x does f of x equal -4? So again, we'll start by setting each piece of the function equal to -4. And solve. So on the left side, we have 3x equals, I'll show my work. So start by subtracting 7 on both sides. So 3x equals -11. Divide by 3 on both sides. X equals -11 over 3. So we got to remember, we have a domain restriction. On this piece of the function, x has to be less than or equal to -2. So -11 over 3 is less than or equal to -2. So this is good. Now, -4 equals -4. That's always true. So if that's always true, well, what x values give us an output of -4? Well, the x values in that part of the domain. So in this case, that's going to be -2 is less than x, which is less than 1. So the solution for this piece is just the domain restriction. Kind of unique, doesn't happen all the time, but every input between -2 and 1 outputs -4. So that has to be part of our solution. And then lastly, we have 6 minus x equals -4. So we subtract 6 from both sides. We have -x equals -10. Divide both sides by -1. X equals +10. And remember, the domain for this piece is x has to be greater than or equal to 1. 10 is definitely greater than or equal to 1. So x equals 10. So for what value or values of x does f of x equal -4? Well, we have a lot of them. X equals -11 over 3. Any x value between -2 and 1. And x equals 10. And again, we can check each of these. The middle part, a little bit tough to check that. There's an infinite number of x values between -2 and 1, but you can try -1 and 0 at least to see if that makes sense, to check and see that you output -4. Hey, so a couple of reminders as we wrap up this video. We looked at evaluating off of a graph and algebraically. Off a graph, we continued with the same technique that we'd been using previously. Algebraically, my advice is to put a box around the domain restriction and treat evaluating a piecewise function as a two-step process. First, determine what domain the input is a part of, and use that to figure out what piece we're going to plug into. As a reminder, these are functions, so every input should only have one output, right? So you should never try to evaluate f of 1 and get 2 answers, okay? Because that doesn't fit the definition of a function. Click the Amazon link down below for my algebra workbook so you can practice on your own. Give the video a like, and before you go, click that subscribe button so you can see more videos just like this. Thanks for watching.